sklearn cluster optics. Description: ordering points to identify the clustering structure. Optics is a density-based clustering algorithm that is similar to DBSCAN but does not require specifying the apes parameter. It produces a hierarchical clustering result. Inputs: data, a numerical array or matrix representing the data points to be clustered. Minsamples: the minimum number of samples or neighbors in a neighborhood for a data point to be considered as a core point. Outputs: reachability distances, an array of reachability distances for each data point, representing the distance to its nearest core point. Ordering of points and ordering of the data points based on their reachability distances. Steps: compute core distances, calculates the core distance for each data point, which is the minimum number of points within a specified radius apes. Find reachability distances for each data point. Calculates the reachability distance, which is the distance to its nearest core point. Order points, sorts the data points based on their reachability distances. Metrics: silhouette coefficient measures the quality of clustering by evaluating how similar a data point is to its own cluster compared to other clusters. Kalinski-Haraba's index measures the ratio of between cluster variance to within cluster variance, with higher values indicating better clustering. Visualization plots: reachability plot, a plot of the reachability distances against the ordering of points, which can be used to identify clusters and noise points. Clustered scatter plot, a scatter plot of the data points, color-coded by cluster membership, to visualize the resulting clusters. Fine-tune parameters: minsamples controls the density threshold for identifying core points. A larger minsamples value requires a higher density for a point to be considered a core point. Maxups: the maximum distance to consider for finding neighbors. Uncertainty methods: probabilistic clustering assigns probabilities to cluster memberships instead of hard assignments. Challenges and fixes: sensitive to minsamples. Use domain knowledge or visualization to estimate appropriate values for minsamples. Perform grid search or other parameter tuning techniques to find optimal values. Computational complexity: can be computationally expensive for large datasets. Consider using approximation methods or faster implementations of the algorithm.